So this class has a lot of both networking and cybersecurity majors, but also software development majors. So I wanted to just kind of talk to the software development side of the house and show you some different things about the Linux system that make it unique, and start with this idea of the different spaces in Linux and what they are. So there are actually two different essentially areas in Linux, and the first is the kernel space. So the kernel is that core that we talked about. This is the actual code that begins to be executed, and and what it does is it creates an environment inside the memory of the computer in order to handle all of the different processes, signals, and other things and communicate with the hardware. So that kernel is the first part I'm going to show you now, and we'll go back to it here. But first, we're going to look at this. This is the interactive version of the Linux kernel, and so we looked at this before in the very first one of our first lectures, but each area of or domain in the computer is down along the bottom axis, and so each of the columns represents one of those domains, whether it's memory or the central processing unit or input-output or a network stack. And then going up this chart is where the abstraction layers occur between as you start at the bottom, you're getting closer to the physical hardware, and as you go up to the top, you're getting closer to the user or the user space. So the interesting thing about this particular map is I actually have what I'm really doing here is I'm able to see the direct code that makes up that kernel. And so at every process, I can see the code base that goes from any area to another. So if I want to look at CPU architecture, okay, um, and I wanted to actually click that Intel initialization, right? So guess what happens? It takes me right into the Bootland site, which is where the code or the code bases are. So on this other side, I have kernel versions. So these are the major versions of the kernel and the releases. And so we have the major uh, and minor revision, and then the release candidate here on the left-hand side. And so when I look at that, I can actually see the where this particular x86 init header file is, and it shows me all of the files where this particular file is referenced. So I can look at the code, and I'm just going to click on a file, and this is the actual code that would go in, and if I was going to compile the kernel, I could download this source code, I could look at it, I could modify it, have it do a certain thing in a certain way, right? Yeah, I could, if I had a bug that I was trying to track down, I could go and actually uh, take that code and modify it, and then compile the kernel. So this is high level code, and it goes through the compiler. And I'm going to look at let's see, I'm going to go look at another um, area, right? So block devices. block device operation. USB storage. So this is a lot less complicated, right? USB storage is only in one file, USB.c. All right, so when I look at that, I can actually go through and look at the actual code that is running in memory that handles the USB storage. So when we talk about open source, this code is by nature and definition entirely open source. I can see every bit of it, and every revision, every modification, right? And so if I wanted to keep this file open and I wanted to see how it changed through the revisions, I could do that and look at it. So once I take this code, and if I'm going to go through the process of compiling the kernel, I actually have to go through and do the compilation. And what I get after that is I get supposing there are no errors, right? As I get a compiled kernel that is one file and it's an executable, and so that file gets loaded up into memory, and it becomes, or it actually begins to be all of the different threads and structures that are needed to run this operating system. So I'm going to go back really quickly, and we're going to look at a very basic idea of compiling code. So I'm going to go to my Windows subsystem for Linux, which I like to use. It's easy to use. So what I've done is in my home folder, I've created a folder called test files. And so when I look at that, I have have some source code here, test.c. Now I'm going to go ahead and list out that code. This is really easy. I mean, it's almost as simple a program as you can get, other than hello world. What happens is this main function starts. We have a variable that we create, an integer, and then we ask the user to enter a number. We use an input function to read the keyboard. We don't, interestingly enough, we do actually do some error checking, because if it's a letter, it's not going to work. But there's no error handling here. So notice there's nothing that says, if this is not a number, then print please enter a number. So there's no error handling, but we just print the number is, and then there it is. We put the output. So that's all that program does. It's very simple. But I'm going to show you how to go about compiling that program. So I use a program called GCC, and I'm going to take my my source code, and I'm going to go ahead and say I'm not going to give it any parameters other than that. Okay, so that program compiles, but we didn't really get any success. We just know that it worked. But what we notice is that when I look in that folder, I have an a.out. Okay, that is that's the default file name of that program. Now I can recompile it, and I'm going to choose a switch -o for output, and I'm just going to say num test. Okay, and now I'm going to list my files again, and I see that I have two files. I have a.out, I have my original source code, and I have num test. Now you'll notice that the color of these two files are different in this case, and I'm going to just kind of look and see why that might be true. So I'm going to go ahead and list my three files, and one of the things that we see is that these two files that are here are actually listed as executable. That's what the X means. It means that the owner and it actually means anybody can run those files. So I'm going to go ahead and do that. In order to execute the file, all I have to do is um, I have to tell it here in this folder is the file I want to run. So I'm going to do num test, and here's my code. Enter a number, 4. Number's 4. Now, just to see what happens if I enter, I hope that if I enter a D or something, I get a runtime error. I'm gonna try it. No, it didn't. It didn't work. It actually overloaded that integer and gave me 0. So, um, yeah, obviously there's some bugs in this code, but as you can see, what I've done is I've created an executable file. So at the point in time which we compiled um, this program, I have taken all of the libraries and functions that I need to have input and output, and I have encoded it in this binary file. So my source code is very small. My binary file is quite a bit larger. But I'm going to go ahead and use the file program and feed it all of the files in this directory and have it tell me what those files are. And we can see that our a.out and our numtest are binary files. Right? This is the ELF is a binary executable, and it tells me in this case it tells me the the Linux system that I use, GNU Linux, and the architecture. It tells me how this is created, dynamically linked, right? And so it's basically ready to run, and it will load those headers at runtime and use them. And then I have this little file right here, the test.c. Notice it's a C source file, right? ASCII text. So that file command will actually look at the files, it'll look inside, it'll try and analyze them and see what's there. But this is an example of taking the source code and compiling it. Now I could take this file and I could move it wherever I want it to go. I can move it to my user bin folder if I want to, and I can have that software there to run and use. Similarly, if I'm using the kernel, my bootloader is going to actually take that kernel and it's going to load it up into memory, and that kernel is going to then spend its time, spend its days, if you will, figuring out, creating a memory map of that whole system, and it's going to be there's going to be all kinds of stuff happening inside that system while it's processing data, while processes are starting and running. And you can kind of see, we can kind of see that the way that works here. I'm going to go ahead and go back to my WSL, and I'm going to use a command called top. And top is basically an examination of the memory and user space. Now, I don't really have a lot going on here, but if I did, if I had maybe a desktop running in the background or a window manager, or if I had the system that was actually serving requests that were coming in from the internet to be handled, I would actually see quite a bit of activity here as I'm looking at the threads and the other information on my system. But just looking at this, we can go to colored mode, which is kind of what I wanted to do there. And there's a lot of key bindings here that I can use to make this actually program a little more useful. But in this case, I'm just watching I'm polling the memory, polling the processes that are occurring. And if there was, like I said, more activity, we would see quite a bit of stuff happening here on this screen. You see data moving and changing. But it does, one thing to see is that it is an active living system that's running inside this machine. So I'm going to go ahead and quit the top program. But that's always there. We would, if we started up our Ubuntu system, we would see, sorry, our Fedora system, we would see much more activity. So I'm going to do that real quick and get that going. And while that's starting up, one thing to know is just a couple commands that when you are when you want to clear your screen, you can use clear. I always list files and I do AL. Now A is going to give me all of the files. L is going to give me details about the files. I like to do that because I get a lot more information. Okay, my Fedora is still starting up, but notice that files that started with a period are showing. That includes the directory that stands for here and the directory that stands for the parent. So if you see, I have these two dots here. That's the parent folder. That's my home folder. So if I use that and do cd dot dot, I'm back in my home folder. I can go to test files into that folder and do an ls. Now, if I do the ls without the AL, I'm not going to get those two dots or the regular dot. That's not going to show up. And actually, no hidden files or folders are going to show up there. Just the ones that are visible are going to show up. Okay, let's see here. I think our OS is loaded. osboxes.org. And one thing about a display manager or window manager is that it does take some time for this to load. It's not immediately fast, but I do want to go ahead and start that because I want some of these systems and devices to actually load into memory. So I'm going to have a login manager, a session manager, window manager, all of these components. I want them to be running because we're going to pop over to the command prompt and we're going to look at the top. So now that I have my desktop up, all right, now what we'll see also is that at some point I'll show you how the different components, so each one of these things are different components that can be loaded at will. This particular bar right here is a component. This app launcher is a component. The search box is a component. The desktop itself is a component. So I'm going to jump over and log in. Now I could do this in another terminal window, but I want to do it in its own window. Now as you can see, we have a lot more processes going on right here, and there's a lot more stuff happening. So this is always kind of moving. But with the desktop actually loaded up, there's just more stuff going on. So this is very similar to if I were to look at the running processes on my Windows machine. I will be able to see it. Couple things that I can see here is that one, I have swap space I'm using 0. I do have some free memory that's not being used. And so as you can see, there are 200 tasks that are happening. One's running, 199 are sleeping. So we get an idea of 2 users, right? And what our CPU load is. Now, if I were to go and actually run a program, I'll go launch Firefox, and then I'll jump over. So you see Wayland right here. That is the window manager that draws things on the screen. So here's a web content and Firefox that are actually the preeminent processes here, and they're running and using up 50% of the CPU power right now. Here's our Firefox. Getting a little bit of sluggishness on my mouse here. Yeah. So as you can see, more memory is being used and more stuff's happening. Uh, System might run a little more sluggishly. But just to show you what's going on there, I'm going to go ahead and quit that. And now this top program doesn't take up much room at all in the memory. Go back to my desktop and log in. I'm probably loading 2 different users at the same time in the session manager, and it's probably not sure it wants to let me do that. So, that's just some ideas. I wanted to show you the difference in the software and what's kind of going on in memory, and also looking at that kernel, so you can really get an idea of just a reminder that I remember the first time I saw the kernel, and I was like, I don't know how they get that code where it comes from, and just to see it in this case, and to look at it and look at it in this wide view of all of things that are happening inside your OS. And this is a map of all the signals that are processed at any given point in time, and it all boils down to this code, which is instructions for how I'm supposed to handle every event that comes up, and how I'm supposed to create the structures in memory in order to do that. It's all right here. So thank you for watching. Hope this was helpful to you.